Hello, in this lecture we'll answer on two questions. In the first question, we will find out the area of this rectangle ABCD, and in the second question, we will find out the area of this vein shape that is inside square ABCD. So, let's start with the first question. In the drawing, we have rectangle ABCD. Inside this rectangle, we have this semicircle. This is called AP. That is equal to 6 units in its length. This is called this is line segment PC. That is equal to 5 units. Again, our mission is to find out the area of this rectangle ABCD. So first of all, those four angles are all right angles because of the fact that ABCD is a rectangle. So this angle is a right angle. This is also a right angle. This is a right angle. And finally, this is also a right angle. In the next step, we define the center of this semicircle. This point is point O. We define the radius of this semicircle as x. We define the touching point of this semicircle with side AB of this rectangle ABCD. This point is point E. And finally, we will define the point of tendency of tangent DC with this semicircle. This point is point M. Point O is the center of this semicircle. Point A is the point of the semicircle itself. Therefore, OA is the radius of this semicircle. That is equal to x units in its length according to our definition. Likewise, OE is also the radius of this semicircle. That is equal to x. We join points O and M together by a straight line. OM is of course the radius of this semicircle. That is equal to x. Because of the fact that the radius OM that equals to x, the radius OM of this semicircle is drawn to point M, that is the point of tendency of tangent DC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If this is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. So, by doing this construction, you can reveal the small quadrilateral DMOA. Inside this small quadrilateral DMOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So, inside quadrilateral MOAD, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle cut a square. So, we learn to this quadrilateral DAOM is rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle DMOA, side MO must be equal to the opposite side DA. But MO is x, therefore the opposite side DA must be also equal to x units in its length. Likewise, in the big rectangle ABCD, the opposite sides must be equal to each other. This is to say, side DA must be equal to the opposite side CB, but DA is x, therefore the opposite side CB must be also equal to x units in its length. In the next step, we will join points P and E together by straight line. By joining points P and E, we created peripheral angle APE. This is peripheral angle APE. Peripheral angle APE subtends on AE, that is the diameter of this semicircle. And we know that according to rule 7, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its size. Repeat again rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. In the moment we have a circle, chord AB is the diameter of this circle. This is peripheral angle ACB that subtends on AB, that is the diameter of this circle, and therefore peripheral angle ACB is equal to 90 degrees in its size. So we can implement all 7 in our drawing. Why? Because in our drawing we have peripheral angle APE that subtends on AE, that is the diameter of this semicircle, and therefore peripheral angle APE must be equal to 90 degrees in its size according to rule 7. We define the size of this angle as alpha, and we focus on the right angle APE. On the right angle APE, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, we focus on the big right angle ABC. On the big right angle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha, according to the same rule that says that the sum of the angles in any triangle is equal to 180 degrees. So, in the next step, we will prove that the big right triangle ABC is similar to this small right triangle APE. So, write it down. We prove that the big right triangle ABC is similar to the small right triangle APE. So why those two right angles are similar to each other? First of all, this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the small right triangle APE, and angle A also belongs to the big right triangle ABC. So we can write down that angle A equals to itself is a common angle that belongs to both triangles. So if we relate to this angle, angle A, since it belongs to the right big triangle ABC, it will be defined as angle CAB. And angle A equals to itself. So if we relate to this angle A, since it belongs to the small right triangle APE, it will be defined as angle PAE. So repeat again. If we found out that this equation means that angle A equals to itself. We just call to angle A two different names. Angle A equals to itself is a common angle that belongs to both triangles. In addition, those two angles, they are both equal to 90 degrees and therefore they are equal to each other. So actually, this is angle ABC. This is angle ABC, the right big triangle ABC. And it is equal to this angle, that is actually angle APE. The right small triangle APE. So repeat again. Angle ABC in the right big triangle ABC equals to angle APE in the small right triangle APE. They are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. This is angle BCA. In the right big triangle ABC, and it is equal to this angle, this is actually angle PEA. In the right small triangle APE. So repeat again. Angle BCA in the right big triangle ABC equals to angle PEA in the right small triangle APE. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I actually found out that all the triangles of the right big triangle ABC are correspondingly equal to all the triangles of this right small triangle APE. And therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big triangle ABC, the big right triangle ABC, is similar. This is the sign of similar to the right small triangle APE according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the right small triangle APE over side AB of the right big triangle ABC is equal to side AE of the right small triangle APE over side AC of the right big triangle ABC. So repeat again. We will derive that side AP of the right big triangle of the right small triangle APE over side AB of the right big triangle ABC equals to side AE of the right small triangle APE over side AC of the right big triangle ABC. AP equals to 6 units in its length according to what is given as the question over AB. AB is the missing side, so we give it as it is, and it is equal to AE. AE is the diameter of this semicircle, that is equal to 2x over AC. AC in totality is 6 plus 5, that is 11. So in total, we shall find out that 6 over AB equals to 2x over 11. And again, 6 over AB equals to 2x over 11. Here we cross multiply this equation, and we get that 6 times 11 is 66, and it is equal to 2x times AB. Here we divide this equation by 2, and we get that 66 over 2 is 33, and it is equal to 2x over 2 is x, so in total this expression equals to x times AB. So here we will divide this equation by x, and we get that AB equals to 33 over x units in its length. So this is side AB of rectangle ABCD, and it is equal to 36 over x units in its length. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. The area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The length of this rectangle ABCD is AB. And the width is CB. So in total, the area of rectangle ABCD must be equal to AB times CB. We have already found out that AB equals to 33 over x times CB. CB equals to x. So in total, the area of rectangle ABCD must be equal to 30x over x times x. We have x in the numerator and x in the denominator, so x will get cancelled, and we left only with 33. So if we found out that the area of this rectangle ABCD, that is the area that we are looking for this question, is equal to 33 square units. Repeat again. We actually found out that the area of this rectangle ABCD is equal to 33 square units. So we finish with the first question. In the next step, I will present to you the second question, and we will solve the second question of this lecture. In this second question, our mission is to find out the area of this green shape. So, in the drawing, we have square ABCD. ABCD is a square. In addition, we know that line segment BP equals to line segment PC. And finally, this is a triangle POC. This is a triangle POC, and the size of this triangle POC is equal to 5 square meters. Again, our mission is to find out the area of this green shape. So first of all, we'll define the length of this line segment BP as A. And because of the fact that BP equals to PC according to what is given as the question, and BP equals to A, therefore PC must be also equal to A units in its length. BC in total equals to A plus A, that is 2A. And you know that all the sides of any square are equal to each other. So if BC equals to 2A, then side AD of square ABCD must be also equal to 2A units in its length. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this vertex angles as theta, then the size of this vertex angles must be also equal to theta because they are equal to each other. We also know that the opposite sides of a square are parallel to each other. So in square ABCD, side AD is parallel to the opposite side BC. Those two angles are defined as alternating angles and are located between the parallels AD and BC. And therefore they are equal to each other according to rule 15. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to rule 15. Likewise, those two angles are also defined as alternating angles and are located between the same parallel lines AD and BC, and therefore they are equal to each other according to rule 15. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta according to rule 15. So in total, we actually found out that those two triangles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to theta, therefore they are equal to each other. Those two angles are both equal to alpha, therefore they are equal to each other, and those two angles are both equal to beta, therefore they are equal to each other. So, in conclusion, we found out that triangle ADO is similar to this triangle POC according to angle similarity rule. So I write it down. Actually found out that the big triangle AOD, the big triangle, the big triangle AOD is similar. This is the sign of similar to the small triangle COP according to angle similarity rule. So in the next step, I will present to you a new rule that relates to similar triangles, and we will implement the new rule in our drawing on those two similar triangles. The new rule is rule 22. According to rule 22, the ratio of the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. Repeat again, the ratio of the areas of similar triangles is equal to the square of the ratio of their corresponding sides. So in the drawing, we have two triangles. Those two triangles, triangle ABC is similar to triangle DEF. And according to this rule 22, the ratio between the areas of those two similar triangles, that is to say, the area of triangle ABC over the area of triangle DEF, is equal to the square of the ratio of their corresponding sides. So what is the square of the ratio of their corresponding sides? And those two triangles, side AC is the corresponding side of side DE. Likewise, side AB is the corresponding side of side DF. And finally, side CB is the corresponding side of side EF. So, side AC is the corresponding side of side DF. So, what is the square of the ratio of those two corresponding sides? is AC over DE squared. The square of the ratio of those two corresponding sides is of course AC over DE squared. Likewise, side AB is the corresponding side of side DF. And the square of the ratio of those two corresponding sides is of course AB over DF squared. And finally, side CB is the corresponding side of side CF. So what is the square of the ratio of those two corresponding sides? It is of course CB over EF squared. Okay, so according to this rule 22, the ratio between the areas of those two similar triangles, that is to say the area of triangle ABC over the area of triangle EDF, is equal to the square of the ratio of their corresponding sides. So we can actually implement rule 22 in our drawing. Why? Because in our drawing we have only found out that this is the big triangle ADO that is similar to this small triangle, triangle COP. And whenever you have two triangles that are similar to each other, you can implement rule 22. So according to rule 22, the ratio between the areas of those two similar triangles, that is to say the area of triangle ADO over the area of triangle COP. Repeat again. The ratio between the areas of those two similar triangles is actually the area of triangle ADO over the area of triangle COP. That ratio according to rule 22 is equal to the square of the ratio of their corresponding sides. So what is the square of the ratio of their corresponding sides? Side AD of triangle ADO is the corresponding side of side PC of triangle POC. Why side AD is the corresponding side of side PC? Because of the fact that side AD is in front of angle theta. Likewise, side PC is also in front of this angle theta. Therefore, side AD is the corresponding side of side PC. And the square of the ratio of those two corresponding sides is of course AD over PC squared. AD over PC squared, the square of the ratio of their corresponding sides. So this equation is the implementation of rule 22 in our drawing. In our two similar triangles, the big triangle ADO and the small triangle COP. The area of this triangle ADO is unknown, so we leave it as it is. The area of triangle ADO over the area of the small triangle COP. The area of this small triangle COP is 5 square units according to what is given as the question. So we will substitute the area of triangle COP by 5, and it is equal to AD over PC. AD is 2A. PC is A squared, so we have to square it. We have A in the denominator and A in the denominator, so A will get cancelled, and we left only with 2 squared, that is 4. So in total, we found out the area of the big triangle ADO over 5 equals to 4. Here we multiply this equation by 5, and we get that the area of the big triangle ADO is equal to 5 times 4, that is 20 square units. So this is the big triangle ADO, and the area of this big triangle ADO is 20 square units. because of the fact that the big triangle ADO is similar to this small triangle COP, the following relationship exists between their sides. Side AD of the big triangle ADO over side PC of the small triangle POC is equal to side AO of the big triangle ADO over side OC of the small triangle POC. Repeat again, from the fact that those two triangles are similar to each other, the following relationship exists between their sides. Side AD of the big triangle ADO over side PC of the small triangle COP is equal to side AO of the big triangle ADO over side OC of the small triangle COP. AD is 2A over PC, PC is A, and it is equal to AO over OC. So in total, we found out that 2A over A equals to AO over OC. We have A in the numerator and A in the denominator, so A will get cancelled, and we left only with 2 in this side of the equation, so 2 equals to AO over OC. Here we multiply this equation by OC, and we get that 2 times OC is equal to AO. Again, 2 times OC equals to AO. We will define the size of OC as B. That is to say, the length of line segment OC equals to B units in its length according to our definition. And we substitute OC by B in this equation, and we get that 2B equals to AO. So we found out that if the length of this line segment OC is B, then the length of this line segment AO is 2B. That is to say, AO is twice as long as OC. Okay, so in the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is Rule 23. According to Rule 23, Rule 23 is true in any triangle. So this is triangle ABC that could be any triangle. So in this triangle ABC that could be any triangle, if from the vertex A we draw the red line segment AP, it will divide triangle ABC into 2 smaller triangles. The first triangle is triangle APB, and the second triangle APC. So Rule 23 talks about the small triangles that were created by drawing line segment AP in triangle ABC. And according to this rule, Rule 23, the ratio between the areas of those 2 small triangles is equal to the ratio between their corresponding bases. So the area of this triangle, so what is the ratio between the areas of those 2 small triangles? It is the area of triangle ABP over the area of triangle APC. The area of triangle APB is equal to the base of the triangle that is BP times the height that is edge over 2. Okay, again, the area of this triangle ABP is equal to the base BP times the height that is edge over 2. Likewise, the area of this small triangle APC is equal to the base PC times the height edge over 2. The base PC times the edge over 2. Both those 2 small triangles have the same height that is edge. So, and the ratio between the areas of those 2 small triangles is of course the ratio between those 2 expressions. And the ratio between those two expressions is this expression. And in this expression, we have edge in the numerator and edge in the denominator, so edge will get cancelled. We have 1 half in the numerator and 1 half in the denominator, so 1 half also will get cancelled. And we have to live with BP over CP. So in total, we have found out that the ratio between the areas of those two small triangles is equal to the ratio between their bases. Why? Because BP is the base of this triangle BPA, and PC is the base of this triangle APC. Repeat again, the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. That is to say, it is BP over CP. Okay, so we can actually implement all 23 in our drawing. Why? Because in our drawing we have the right big triangle ADC. In this right big triangle ADC, we have line segment OD that divides the big triangle ADC into two smaller triangles. The first small triangle is triangle ADO, and the second small triangle is triangle ODC. So all the requirements of Rule 23 are satisfied, and therefore we can implement Rule 23. According to Rule 23, the ratio between those two small triangles that were created by drawing line segment OD in triangle ADC, the ratio between the areas of those two small triangles, that is to say, what is the ratio between the areas of those two small triangles, is actually the area of triangle ADO is the area of triangle ADO over the area of this triangle OCD. This expression is actually the ratio between the areas of those two small triangles that were created by drawing line segment OD in triangle ADC. And the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. The base of this triangle ADO is AO, and the base of this triangle OCD is OC. And the ratio between their corresponding bases, it is actually the base AO of triangle AOD over the base OC of triangle COD. So in total, we have found out that the ratio between the areas of the two small triangles is equal to the ratio between their corresponding bases. So this equation is the implementation of Rule 23 in our drawing. In our drawing, this is actually the big right triangle ADC. Okay. The area of this triangle ADO is 20 square units. So we substitute the area of triangle ADO by 20 over the area of this triangle OCD. The area of this triangle is unknown, so we leave it as it is. This is the area of triangle OCD, and it is equal to AO. AO is 2B over OC. OC is B. So in total, we have found out that 20 over the area of triangle OCD is equal to 2B over B. We have B in the numerator and B in the denominator, so B will get cancelled, and we left only with 2. So in total, we have found out that 20 over the area of triangle OCD is equal to 2. Here we multiply this equation by the area of triangle OCD, and we get that $20 equals to 2 times the area of triangle OCD. Okay, after multiplying this equation by the area of triangle OCD, we found out actually that 20 equals to 2 times the area of triangle OCD. Here we will divide this equation by 2, and we get that 20 over 2 is 10, so 10 equals to the area of triangle OCD. That is to say, the area of triangle OCD is equal to 10 square units. So I have found out that the area of this triangle OCD is equal to 10 square units. It's very easy to say from the drawing that the area of the right triangle ABC, actually that the triangle ABC can go into triangle ADC. Those two triangles can go into each other according to side rule. That is to say, side AB of triangle ABC is equal to side DC of triangle ADC. Why? Because it is a square. And remember, all the sides in a square are equal to each other. Likewise, side BC of triangle ABC is equal to side AD of triangle ADC for the same reason. Because it is a square. And finally, side AC is a common side that belongs to both triangles. So we can write down that AC equals to itself is a common side that belongs to both triangles. So in total, we actually found out that triangle ABC, the right triangle ABC, can go to the right triangle ADC according to side rule. So I write it down. We actually found out that the big right triangle ABC congruent, this is the sign of congruent, to the right big triangle ADC according to side rule. And from the fact that those two right triangles can go into each other, we derive that they have also the same areas. Why? Because of the fact that any two right triangles that can go into each other, they must have the same areas. Therefore, we shall find out that the area of triangle ABC is equal to the area of triangle ADC. But again, whenever you have two triangles that can go into each other, they must have also the same areas. But the area of this right big triangle ADC, in total it is equal to 20 plus 10, that is 30 square units. So you can write here that the area of triangle ADC is equal to 30 square units. It is very easy to see it from the drawing. So in total, we shall find out that the area of triangle ABC is equal to the area of triangle ADC, and it is equal to 30. From this equation, we will derive that the area of triangle ABC is equal to 30. Okay? The area of triangle ABC is equal to 30 square units from one side, but from the other side, the area of this triangle ABC, what is the area of this triangle ABC? The area of triangle ABC is equal to the area of the green chip plus the area of this triangle POC. So we define the area of this green shape, that is the area that we are looking for in this question, as x, that is to say the area of the green shape is equal to x square units according to our definition. Therefore, in total, the area of this triangle ABC from the other side is equal to x plus 5 square units. So from the other side, we actually found out that the area of triangle ABC is equal to x plus 5 square units. And from this equation, x plus 5 equals to the area of triangle ABC equals to 30. We will derive that x plus 5 equals to 30. Here we subtract 5 from this equation. And finally we get that x equals to 30 minus 5 is 25. 25 square units. So actually, in conclusion, we should find out that x is the area of this green shape. So in total, we should find out the area of this green shape that is there that you are looking for this question is equal to 25 square units. So we finish with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. Our mission in the first question is to find out the area of this rectangle ABCD. So in the drawing we have rectangle ABCD. Inside this rectangle we have this semicircle. In addition, we know that this is called AP, that is equal to 6 units in its length. This is line segment PC, that is equal to 5 units. Again, our mission is to find out the area of this rectangle ABCD. First of all, because of the fact that ABCD is a rectangle, all those 4 angles inside the rectangle ABCD are right angles. In the next step, we define the center of this semicircle. This point is point O. We define the touching point of this semicircle with side AB of rectangle ABCD. This point is point E, and we define the point of tendency of tangent. We define the point of tendency of tangent DC with this semicircle. This point is point M. We also define the radius of this semicircle as X. So here point O is the center of this semicircle, point A is the point on the semicircle itself, therefore OA is the radius of this semicircle, that is equal to X. Likewise, OE is also the radius of this semicircle, that is equal to X. We join points O and M together by straight line. OM is of course the radius of this semicircle, that is equal to X. And because of the fact that the radius OM that is equal to X, the radius OM is drawn to point M, that is the point of tendency or tangent DC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If this is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. By doing this construction, we continue the small quadrilateral DMOA. Inside this small quadrilateral DMOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the small quadrilateral DMOA, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle plus a square. So we relate to this small quadrilateral DMOA is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle DMOA, side MO must be equal to the opposite side DA. But MO is X, therefore the opposite side DA must be also equal to X units in its length. Likewise, in the big rectangle ABCD, the opposite sides must be also equal to each other. That is to say, side DA must be equal to the opposite side CB. But DA is X, therefore the opposite side CB must be also equal to X units in its length. In the next step, we join points P and E together by straight line. By joining points P and E, we created peripheral angle APE. This is peripheral angle APE that subset on AE, that is the diameter of this semicircle, and we know that according to rule 7, any peripheral angle that subset on the diameter of the circle or semicircle must be equal to 90 degrees in its size. Therefore, this peripheral angle APE is equal to 90 degrees in its size according to rule 7. We define this angle as alpha, so in the right angle APE, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this first missing angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that those two right triangles similar to each other according to angle similarity rule. That is to say, we prove that the big right triangle ABC is similar to this small right triangle APE. So when those two right triangles are similar to each other. First of all, this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the big right triangle, ABC, and angle A also belongs to the right small triangle APE. So we can find out that angle A equals to itself is a common angle that belongs to both angles. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees and so far, therefore they are equal to each other. So we should prove that all the figures of the right big triangle APE are correspondingly equal to all the figures of the right big triangle ABC are correspondingly equal to all the figures of the right small triangle APE. Therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the right small triangle APE over side AB of the right big triangle ABC is equal to side AE of the right small triangle APE over side AC of the right big triangle ABC. So together we derive that side AP of the right small triangle APE over side AB of the right big triangle ABC equals to side AE of the right small triangle APE over side AC of the right big triangle ABC. AP is 6 according to what is given in the question. AB is the missing side, so we leave it as it is, and it is equal to AE. AE equals to 2x, it is the diameter of the semicircle, it is equals to 2x. Over AC, AC in total is 6 plus 5, that is 11. So in total, we should find out that 6 over AB equals to 2x over 11. Here we first multiply this equation and finally found out that 6 times 11 is 66, and it is equal to 2x times AB. Here we divided this equation by 2 and finally found out that 66 over 2 is 33, and 2x over 2 is x, so in total this expression equals to x times AB. Here we divided this equation by x and finally found out that AB equals to 33 over x. So if we found out that the length of this side AB of rectangle ABCD is equal to 33 over x units. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of a rectangle equals to the length of the rectangle. The area of a rectangle is equal to the length of the rectangle times the width. And therefore the area of this rectangle ABCD must be equal to the length of this rectangle ABCD times the width. The length of this rectangle ABCD is AB and the width is BC. So in total, the area of rectangle ABCD must be equal to the length AB times the width CB. AB is 33 over x and CB is x. So in total, the area of rectangle ABCD must be equal to 33 over x times x. We have x in the numerator and x in the denominator, so x will get cancelled, and we left only with 33. So in total, we should find out the area of this rectangle ABCD is equal to 33 square units. We finish with the first question. In the next step, I presented to you the second question, and we solve the second question of this lecture. Our mission in the second question is to find out the area of this grand shape. So in the drawing, we have square ABCD. This is line segment BP that equals to line segment PC. We also know that this is triangle OCP that is equal to 5 square units in its size. Again, our mission is to find out the area of this grand shape. First of all, we define the length of this line segment BP as A, and because of the fact that BP equals to PC, PC must be also equal to A. So total BC equals to A plus 8, it is 2A. And we know that all the sides of any square are equal to each other. So if BC is 2A, then AD must be also equal to 2A units in its length. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if the size of this angle is theta, then the size of this angle must be also equal to theta because they are equal to each other. We know that the opposite sides of a square are parallel to each other. So in square ABCD, side AD is parallel to the opposite side BC. Those two angles are defined as alternating angles and they are located between the parallel lines AD and BC, and therefore they must be equal to each other according to Rule 15. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to Rule 15. Likewise, those two angles are also defined as alternating angles and they are located between the same parallel lines AD and BC, and therefore they must be equal to each other according to Rule 15. So if the size of this angle is beta, then the size of this angle must be also equal to beta, according to Rule 15. So in total, if you found out that all the fingers of this big triangle AOD are correspondingly equal to all the fingers of this small triangle POC. In both triangles we have angle alpha, in both triangles we have angle theta, and in both triangles we have angle beta. So those two triangles are similar to each other according to angle similarity rule. In the next step, I presented to you a new rule that relates to two similar triangles, and we implemented the new rule in those two similar triangles, ADO and POC. The new rule is Rule 22. So repeat quickly on Rule 22. According to Rule 22, the ratio of the areas of similar triangles is equal to the square of the ratio of their corresponding sides. So, in the drawing we have two similar triangles. Triangle ABC is similar to triangle DEF, and according to this rule, Rule 22, the ratio between the areas of those two triangles, that is to say, the area of triangle ABC over the area of triangle EDF, is the ratio between the areas of those two similar triangles. That ratio is equal to the square of the ratio of their corresponding sides. What is the square of the ratio of their corresponding sides? Here, side AC is the corresponding side of side DE. Likewise, side AB is the corresponding side of side DF, and side CB is the corresponding side of side EF. So, side AC is the corresponding side of side DF. So, what is the square of the ratio of those two corresponding sides? It is actually AC over DE squared. AC over DE squared. Likewise, side AB is the corresponding side of side DF. So, the square of the ratio of those two corresponding sides is of course AB over DF squared. And finally, side CB is the corresponding side of side EF. So the square of the ratio of those two corresponding sides is of course CB over EF squared. So, according to Rule 22, the square of the ratio of those two, according to Rule 22, the ratio between the areas of those two similar triangles is equal to the square of the ratio of their corresponding sides. So we can actually implement Rule 22 in our drawing. Because in our drawing, we have already found out that the big triangle AOD is similar to the small triangle COP. And whenever you have two triangles that are similar to each other, you can implement Rule 22. According to Rule 22, the ratio between the areas of those two similar triangles, that is to say, what is the ratio of the areas of those two similar triangles, is actually the area of triangle ADO over the of triangle COP. That ratio is equal to the square of the ratio of their corresponding sides. Side AD of triangle ADO is the corresponding side of side PC. Why side AD is the corresponding side of side PC? Because of the fact that AD is in front of angle theta, this triangle ADO, and PC is also in front of angle theta in this small triangle POC. Therefore, AD is the corresponding side of side PC, and the square of the ratio of their corresponding side is of course AD over PC squared. So in total, if we found out that according to Rule 22, the ratio between the areas of the two similar triangles is the area of triangle ADO over the area of triangle COP, and it is equal to the square of the ratio of their corresponding sides. The square of the ratio of their corresponding sides is AD over PC squared. So this equation is the implementation of Rule 22 in our drawing. the area of triangle ADO is unknown, so leave it as it is, over the area of the small triangle COP. It is given as the question that the area of this small triangle COP is equal to 5 square roots. So we substitute the area of triangle COP by 5, and it is equal to AD over PC squared. AD is 2A, PC is A. AD over PC is 2A over A squared. We have A in the numerator and A in the denominator, so A will get cancelled, and we left only with 2 squared, that is 4. So in total we shall find out that the area of triangle, the big triangle AD over 5 equals to 4. Here we multiply this equation by 5 and finally found out that the area of the big triangle ADO is equal to 5 times 4, that is 20. And again we shall find out the area of this big triangle ADO is equal to 20 square units. Because of the fact that triangle ADO is similar to this triangle POC, the following relationship exists between the sides. Side AD of triangle ADO over side PC of triangle POC is equal to side AO of triangle ADO over side OC of triangle POC. But again, side AD of the big triangle ADO over side PC of the small triangle POC is equal to side AO of triangle ADO over side OC of triangle POC. AD is 2A and PC is A. Again, AD is 2A and PC is A. We have A in the numerator and A in the denominator, so A gets cancelled. So in this side of the equation we left only with 2. It is equals to AO over OC. Here, so 2 equals to AO over OC. Here we multiply this equation by OC and we found out that 2 times OC equals to AO. 2 times OC equals to AO. We define the length of side OC as B. OC equals to B according to our definition. And we substitute OC by B in this equation and finally found out that 2B equals to OA. So actually found out that if the length of this side OB is B, then the length of side OA is 2B. That is to say, OA is twice as long as OB. Okay, so in the next step, I presented to you a new rule and implemented the new rule in our drawing. The new rule is rule 23. So first of all, rule 23 is true in any triangle. This is triangle ABC that could be any triangle. In this triangle ABC, if you draw the red line segment AP, it will divide triangle ABC into 2 smaller triangles. The first triangle is triangle ABP and the second triangle is triangle ABC. Rule 23 talks about the small triangles that were created by drawing line segment AP in triangle ABC. According to this rule 23, the ratio between the areas of those 2 small triangles is equal to the ratio between their corresponding bases. So we are talking about the ratio between the areas of those 2 small triangles. So that is to say, the area of this triangle ABP over the area of this triangle APC. That is the ratio between the areas of those 2 small triangles. The area of this triangle ABP is equal to the base BP times the height edge over 2. So the area of this triangle ABP is the base BP times the height edge over 2. Over the area of this triangle APC. That is the ratio between the areas of those 2 small triangles. So what is the area of this triangle APC? It is equal to the base BC times the height edge over 2. The area of this triangle APC is equal to the base BC times the height edge over 2. So both triangles have the same height edge. So the ratio between the areas of those 2 small triangles is of course equals to the ratio between the areas of those 2 expressions. So the ratio between those 2 expressions is this expression. And we have edge in the numerator and edge in the denominator, so edge will get cancelled. We have 1/2 in the numerator and 1/2 in the denominator, so 1/2 will also get cancelled. And we left only with BP over CP. BP over CP. So in total, we shall find out that the ratio between the areas of those two small triangles, that is actually the area of triangle ABP over the area of triangle APC, is equal to the ratio between their corresponding sides. BP is equal to the ratio between their corresponding bases. BP is the base of triangle ABP, and PC is the base of triangle APC. And the ratio between their corresponding bases is, of course, the base BP of triangle APC, ABP over the base PC of triangle APC. So in total, we found out that the ratio between the areas of those two triangles is equal to the ratio between their corresponding bases. That is to say, the area of triangle ABP over the area of triangle APC equals to the base BP over the base CP. Okay, so we can actually implement rule 23 in our drawing. Why? Because in our drawing we have, this is the big right triangle ADC. In the big right triangle ADC, we have line segment OD that divides triangle ADC into two smaller triangles. The first small triangle is triangle ADO, and the second small triangle is triangle ODC. So all the requirements of rule 23 are satisfied, and therefore we can implement here rule 23. According to rule 23, the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. So the ratio between the areas of those two small triangles is equal to the area of triangle ADO over the area of triangle OCD. That is the ratio between the areas of the two small triangles, and that ratio is equal to the ratio between their corresponding bases. The base of triangle ADO is AO, and the base of triangle OCD is OC. And the ratio between the corresponding bases is, of course, AO over OC. So the ratio between their the ratio between their areas, the ratio between the areas of the two small triangles, that is the area of triangle ADO over the area of triangle OCD, equals to the ratio between their corresponding bases, that is AO over OC. Because AO is the base of triangle ADO, and OC is the base of triangle OCD. So in total, we shall find out that the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. So that is to say, it is the area of triangle ADO over the area of triangle DOC, that is the ratio between the areas of the two small triangles, and it is equal to the ratio between their corresponding bases, that is AO over OC. The area of triangle ADO is 20, so we substitute the area of triangle ADO by 20 over the area of triangle ODC. The area of triangle ODC is unknown, so we left it as it is. And it is equal to AO over OC. AO is 2B and OC is B. So AO over OC is 2B over B. We have B in the denominator and B in the denominator, so B will get cancelled, and left only with 2. So total, we actually found out that 20 over the area of triangle OCD equals to 2. If we multiply this equation by the area of triangle OCD, and finally found out that 20 equals to 2 times the area of triangle ODC. If we divided this equation by 2, and finally found out that the area of triangle OCD is equal to 20 over 2, that is 10. This is triangle OCD, and the area of this triangle OCD is equal to 10 square units. It is very easy to see from the drawing that the big right triangle ABC can go to the right small triangle ADC. So why those two right triangles can go into each other? Because of the fact that ABCD is a square, all of its sides are equal to each other. So why those two right triangles can go into each other? First of all, side AB of triangle ABC is equal to side DC of triangle ADC because it is a square. Likewise, side BC of triangle ABC is equal to side AD of triangle ADC for the same reason. And finally, side AC is a common side that belongs to both triangles, so I can write down that side AC equals to itself as a common side that belongs to both triangles. So in total, we shall find out that triangle ABC can go to triangle ADC according to side rule. Triangle ABC can go into triangle ADC according to side rule. And for the fact that those two right triangles can go into each other, we will derive that they are also the same areas. That is to say, the area of this triangle ABC is equal to the area of triangle ADC. The area of triangle ABC is equal to the area of triangle ADC. Whenever you have two triangles that can go into each other, they must have also the same areas. Therefore, the area of triangle ABC is equal to the area of triangle ADC. But it is very easy to see from the drawing that the area of this triangle ADC equals to 20 plus 10, that is 30 square units. So you can write here that the area of triangle ADC is equal to 30 square units, and from this equation, the area of triangle ABC equals to the area of triangle ADC equals to 30. We will derive that the area of triangle ABC is equal to 30 square units. So the area of this triangle ABC is equal to 30 square units from one side. But from the other side, the area of this triangle ABC is equal to the area of the green shape plus the area of triangle POC. So we define the area of the green shape as x, that is to say the area of this green shape is equal to x square units according to our definition. And the area of triangle POC is 5. So in total, the area of triangle ABC will be equal to x plus 5 square units. So from the other side, the area of triangle ABC is equal to 30 square units. From one side, the area of triangle ABC equals to 30 square units, and from the other side, the area of triangle ABC equals to x plus 5 square units. Again, this right triangle ABC equals to x plus 5 square units. So from the other side, the area of triangle ABC equals to x plus 5 square units. So in total, we have found out that x plus 5 equals to the area of triangle ABC equals to 30 square units. And from this equation, we derive that x plus 5 equals to 30. Here we subtract 5 from this equation, and finally found out that x equals to 30 minus 5 is 25. So we found out that the area of this in shape that is there that we are looking for in this expression is equal to 25 square units. Okay, thank you very much.